So consider the subset vanishing set of x, y, which lies in A2. Now this is union of two closed sets, vanishing set of x and vanishing set of y. So this is the vanishing set of x. This is x equals to 0. So this is vanishing set of x, and this is x-axis, which is y equals to 0. So this is vanishing set of y, and both of these axes correspond to the equation xy equals to 0. So that is vanishing set of xy. So you can see this vanishing set of xy is actually has two proper parts, vanishing set of x and vanishing set of y. So these are two proper subsets. So this is reducible, or you can say not irreducible. So now we want to define irreducible set. So this is reducible, we want to define irreducible. So a set, algebraic set x is irreducible if you can write x as x1 union x2, then x is equal to x1 or x is equal to x2. So if x is equal to x1, then x2 would be a null set. If x is equal to x2, then x1 would be a null set. So in this case, these vanishing set x and vanishing set y are both proper sets. None of them are null. You can see them in the figure here. So none of them are null sets. So this is not irreducible. So you take an algebraic set x and it is not empty, then x is irreducible if and only if its corresponding ideal is prime. So the way we are going to prove it is we are going to say contrapositive, that is not irreducible x, that is x is reducible if and only if this I of x is not prime. So we are using contrapositive. So these two statements are the same by contrapositive. So let us do this first, this part. X is reducible or not irreducible x would imply I of x is not prime. So for this, you decompose x into two parts, x1 union x2. So both of them are proper sets, none of them is empty. So x obviously contains x1, it properly contains x1. So this is a strict inclusion, and x also contains x2. This is also a strict inclusion. Now you apply the ideal to it. So ideal of x will be contained in ideal of x1, ideal of x will be contained in ideal of x2. Notice these signs have reversed. This is reversed right here, this is reversed right here. Now you consider a polynomial f. This lies in ideal of x1, but it does not lie in ideal of x. And you consider another polynomial g. This lies in ideal of x2, but it does not lie in ideal of x. But you will notice that fg lies in the ideal of x. Now this is because f times g vanishes on x. Now this is obvious. So consider fg on x1 union x2. So obviously this x1 union x2 we have taken as x. So on x1, this f times g becomes 0 times g, because f vanishes on x1, because we have taken f from ideal of x1. So f will vanish on x1, so this becomes 0 times g, which is 0. So fg vanishes on x1. Similarly, on x2, g vanishes. If you take on set x2, this f times g becomes f times 0, because g becomes 0 on x2, because g has been taken from ideal of x2. So f times 0 will become 0. So f times g vanishes on x1 union x2. Therefore, f times g lies in the ideal corresponding to this algebraic set x. So thus ideal of x is not prime, because you have taken f which does not lie in I of x, g which does not lie in I of x, but their product lies in ideal of x. Now in the other direction, this direction, I of x is not prime, and this will imply x is not irreducible. So we are going to show that I of x is not prime, and we will end up as this algebraic set x has a proper decomposition as two algebraic sets. So that is vanishing set of some ideal union vanishing set of another ideal. So I of x is not prime. That means there are two polynomials f and g. They do not lie in the ideal, but their product f times g lies in this ideal. Now you construct a bigger ideal which contains I of x. So I of x is contained in the ideal which is generated by all the elements of I of x, and you adjoin f to those elements. So this is a bigger ideal which contains I of x, and it also contains f. I of x also naturally lies in this ideal which contains all the polynomials in ideal of x, but also g. Obviously f and g are not lying in ideal of x, but you are now adjoining g here, you are joining f here. Now you apply the v operator to it, so these signs will reverse. So this sign becomes this sign becomes this sign, and we are just putting v in front of everything. So first notice that vanishing set of ideal of x is just x. So this is because x is an algebraic set. So x is algebraic set, and this we showed in a previous lecture that this equality holds. Everything else is nothing. We have just put a vanishing set here. We got this, copied this thing exactly here, put a vanishing set in front of it, copy exactly this thing here, you put a vanishing set in front of it, and these signs have reversed. Now you pick a point p in x. So then we have f times g of p is 0. Yeah, obviously because f times g lies in the ideal of x, so f g p would be 0. F times g has to vanish on x. So thus either f of p is 0 or g of p is 0. So if f of p is 0, then this point will lie in the algebraic set corresponding to this ideal which contains f, or this point will lie in the ideal which contains g and obviously contains all the elements of ideal of x. And this implies that x is equal to vanishing set of ideal of x comma f union vanishing set of ideal of x comma g. Obviously because the point, you take any point in x, it either lies in this set because it either corresponds to f equals to 0, or it lies in this set, that is, it corresponds to g equals to 0. So there is a proper decomposition. None of them are null sets. So x then becomes not irreducible or reducible. Now we make a small remark which we are going to use in a proposition soon. So consider this chain, this decreasing chain of sets. So x1 contains x2, which say in turn contains x3, so on all the way to say it contains xk, and this chain goes on. Now you apply ideals to it, these signs will reverse, these inclusion signs will reverse. So ideal of x1 is contained in ideal of x2, which is contained in ideal of x3, all the way to ideal of xk, and so on. Now we are working in a Noetherian ring. Yeah, again recall that we are working in this ring. This k is a field here, so this thing is a Noetherian ring. So this must stabilize. This must stabilize for some n. So after some n it will stabilize, that is ideal of xn will become equal to ideal of xn plus 1. For some n it will stabilize. So say it stabilizes here, I of xn, and so then corresponding to it, this sequence of sets will also become stationary. So we will also have somewhere stability here. You have xn, then you will have equal to xn plus 1, and so on. So thus every sequence of closed sets which is like this becomes stationary and has a minimal element. So the minimal element here will become xn, just corresponding to this ideal here. So now we come to a proposition. So the proposition is that you take an algebraic set, you can decompose it like x1 union x2 all the way to union xn, where each of these xi's is irreducible. So x1 is irreducible, x2 is irreducible, x3 is irreducible, and so on. That is, each xi is irreducible. And the second thing is that this decomposition into irreducible components is unique. So let us start with existence. So we start with existence. So say S is a set of closed sets not having such a representation. So it consists of sets like say y y is y1 union y2, so on, such that this yi is reducible. So this thing is reducible. Now this set will have a minimal element. So by this logic above, it will have a minimal element. So you had a minimal element here. This will also have a minimal element, say m. Now this m can be decomposed into smaller sets m1 and m2. So this minimal element m, you can write it as m1 union m2. Now if m1 and m2 are reducible, this m1 and m2 are reducible, then there is a contradiction, because m1 and m2 are both smaller than m. They are both smaller than m, so it contradicts the minimality of m. On the other hand, if m1 and m2 are irreducible, then you can express m as m1 union m2, where both of them are irreducible. Then m does not lie in this set S, because this set has closed sets which do not have a representation like this m1 union m2 into irreducible elements. So in either case you will have a contradiction. Therefore you cannot have closed sets like this which will not have a decomposition in irreducible elements. So again, this x is x1 union x2 all the way to union xn. Each of these are irreducible, and we have just shown the existence. Now we will show the uniqueness. Now we focus on the uniqueness. So consider this algebraic set X has two decompositions. One is x1 union x2 xn, so all the i's, and the second is in terms of some sets y, so union of y k, so over k. So we want to show that there is actually a unique decomposition. So some xi has to be equal to some yi here. So first you take this xi, take a particular xi. So say you picked up x2. So here for generality we are picking up xi, so you could think of picking up x2. So you pick up this xi and you cover it with these sets y of k. So union of xi intersection y of k. But we have said before that each of these xi is irreducible. So you cannot properly decompose it. So this xi will lie within some yj. So it will not lie in different sets, but in some y of j, because each of these yks are also irreducible. So it cannot lie in different irreducible sets. It has to lie within one irreducible set. So it lies within y of j. So xi is xi intersection y of j. In particular, you see we have this inclusion here. Xi is contained within y of j. Now you reverse it. You focus on this y of j. So we have said this y of j is important to us. So you focus on this y of j. So focus on this y of j. And this y of j, now you cover it with xi's. So union xi intersection y of j. Now again, y of j is irreducible, because once you make a cover, this cover has to be irreducible. So this y of j is irreducible. So y of j would be y of j intersection some irreducible x of m. So in particular, this y of j will lie within x of m. Now x of I is irreducible, x of m is irreducible. You have to have I equals to m. And so if xi is equal to xm, then xi is also equal to y of j. So this inclusion becomes equality. So xi is equal to y of j. So this is the proof for uniqueness.